Well, the main reason why we use epoxy resin is because it's very strong. It's a very good electrical insulator. It's strong and it's available. So that's why epoxy became the sort of de facto standard for these materials. It's also possible to bond it to glass fibers very, very well. Also, the glass fibers that we use have special treatments on the surface that actually will form a chemical bond directly through what's called a silane treatment to the epoxy resin. So we're not talking of mechanical connections here, we're talking of chemical connections. So we can actually chemically link the resin to the glass fibers so they don't fall apart, and that's a very important thing. So epoxy came around for those reasons. Epoxy resins are used in many things. I'm sure we know in construction. They're used in paints, they're used in tin can coatings. Inside of cans are coated with epoxy resin. It's very resilient. It doesn't have a particularly high water absorption. It's very strong and it's available. That's the main reason why we use epoxy. The other resins that are around, I mean, if we think back, to a few years ago when all this started, I mentioned phenolic resins. They were the sort of low grade, cheaper materials. Epoxy resins took the kind of professional part of the market, but there were other kinds as well. And we used to classify our materials based on the chemistry. We would have other materials like a material called polyimide material, for example, which going back 20 or 30 years was the only material really available that would survive very high temperatures of soldering. So it's used typically in military and aerospace applications where you want to be able to repair these articles in the field with soldiers, using pretty uncontrolled equipment, so pretty robust. They call it soldier-proof material. So that was a standard. And then, of course, there are other things came along that people were concerned about signal integrity at some stage. So a lot of these materials are quite lossy. When I say lossy, what I mean is when you input a signal through them, you lose part of that signal. The reason for that is that the structures of them are quite polar. So it's possible for the material to actually absorb energy from the signal. So materials that are not polar, like PTFE, for example, came along. PTFE is very unpolar because it has a backbone of hydrogen with fluorine atoms distributed along it. Fluorine is a very electronegative compound, atom. So this structure forms itself rigidly in place. It really can't move around. The atoms are locked in position. And if they're locked in position, they can't move. If they can't move, they can't expend energy or consume energy. So there's a whole range of materials that came along like that. So if we think back to the beginning, so we have phenolic resins, we have epoxy resins, we have polyimide resins, and we have PTFE resins. And these are kind of, if you like, the starting place where we came from. But of course, over time, people have said, well, actually, I quite like the epoxy. It's really good. It's very good to process. It works really well. But I wish it was a bit less lossy. So, of course, people started to work on it. I said, okay, let's see if we can do something about that. So they reformulated some of these materials to make them less lossy, for example. Or they said, I like PTFE. It's a great material. The loss is wonderful, but I can't really process it very well. So couldn't you make it a bit like the loss, but give me a better process? Couldn't you work on that? So yes, we can do that. So chemists started to work again. So over time, you found a kind of, let's say, a derivation of all these materials, and all of them have been tweaked substantially to change for the properties that are required for today's market.